So how do you think this circuit will behave? You see that this circuit consists of an operational amplifier right over here. It has got two resistors, R1 and R2, both have a value of 10k each. Then it has got two capacitors with a value of 220 nanofarad each. So we have an input signal V in and we have an output signal V out for this circuit. So we want to analyze the behavior, that is quantitative behavior of this circuit. So we clearly can observe the operational amplifier is biased or configured in such a way that its output is tied back to the negative pin of the amplifier, so that makes it configured as a voltage follower circuit, or in other words we say op-amp act here as a buffer between input and the output pins of the amplifier. Advantage of using such configuration of op-amp is that it provides extremely high input impedance at the input side and it provides extremely low output impedance at the output side. Having an extremely high input impedance at the input side implies that the op-amp can be driven with negligible amount of current, and having an extremely low output impedance of the amplifier implies that the op-amp offers large amount of current to be delivered to the load. So that's the advantage of using it as a buffer or voltage follower, and the output voltage is equal to the voltage applied or available at the positive pin of the op-amp. That's why it's called voltage follower. So we don't really have a gain because output divided by the input is equal to 1. That's why we call it as a voltage follower. Output voltage follows the voltage at the input. Now this voltage follower property with extremely high input impedance and extremely low output impedance comes due to the advantage of a very high open loop gain of the op-amp that can be indicated by a letter A right over here. So we know that the gain of the amplifier is the ratio of output divided by the input of the op-amp, that is, let's say VD, where VD is the differential voltage between positive and the negative pin of the amplifier. Okay, so, or in other words we just say VI is the difference between the positive and the negative pin of the amplifier. So since we say that A is equal to V out divided by VI, we can also write VI is equal to V out divided by A. So A comes here and VI goes right over here. Okay, so now if the gain of the amplifier, so let me write here V out divided by A is equal to VI, where VI is the difference between the two input pins of the amplifier. So if the gain is assumed to be very high, ideally infinity, that means the differential input voltage VI has to be 0, and that implies there is no difference between the voltages applied at the positive and the negative pin of the amplifier. We say that the op-amp output voltage will be 0 and gain is infinite, as we assumed earlier. So that's the behavior of your operational amplifier that we have found out. Okay, now what we need to understand, let's say we have an input signal here and it has got a peak or peak to peak amplitude of the signal, and it has got a certain frequency, let's say called f. Let's say it has got the frequency f. Now there are impedances of the circuit offered by C1, C2, R1 and R2, and there is a pole frequency, or also called as cutoff frequency, omega, let's say omega, which is equal to 1 over square root of R1, R2, C1 and C2. If the R1 and R2 are of same value, which is right here in the circuit, and C1 and C2 are of same value, which is as shown in the circuit, then this expression can be reduced to 1 over R times C. So omega is the cutoff frequency or the pole frequency of this filter, and we say that if the input frequency f is omega, then in this case will be 2 pi f, which will be 2 pi f. So we'll say that if the input frequency f is very less than fc or omega c, whatever you say. So let me write here, if the input frequency f is very less than fc, we want to understand how the circuit will behave. So if the frequency is very low, the capacitance impedances are extremely high. That means capacitor C1 and C2 behaves as an open circuit. So when this C1 is open, Vi is blocked, it cannot get transferred further. Okay, and C2 is also open, so obviously it is also an open circuit, no signal can pass further. So that's the behavior. Okay, so we see that output obviously will be equal to 0. However, if the input signal frequency is very greater than fc, capacitors impedances are extremely low, making C1 and C2 behave as a short circuit. So when then there is a short, we see that the circuit only has resistor R1 and R2, and there is this signal is also coming to the positive pin, and due to the voltage follower property, V out is equal to the input signal V in, and we would say this output is being fed back to the positive pin also, and the capacitor C2 is short, so there is this positive feedback. And so with this we can see that the behavior is like this. The plot would be like this. This is the gain, that is the ratio of output divided by this input, and on the x-axis we have frequency though, so the frequency response will look like this. So this is when the frequency is very greater than fc, and this section is when the frequency of the input is very less than fc, and somewhere in the middle you have f equal to fc, where the gain is slightly less than the unity. That is the response, therefore, is of high pass filter, and this is a sallen-key second order active high pass filter topology. Okay, so hope you found this module useful. If you did so, share it with others and stay tuned for more informative contents like this. Till then, wish you happy learning. One more important point, if I ask you to compare this circuit with this circuit, can you spot the difference? you can see that instead of the capacitor in the previous circuit, I now have got the resistor here. Instead of C2 I have R2 here, instead of R1 I have C1 here, instead of R2 I have got C2 here. So I have simply interchanged the position of resistors and capacitors of the previous circuit with these new positions. So this circuit will behave in certain way, which we have explained in our previous module. So you can refer to that module, as well as if you don't want to refer to that module, you can simply solve and analyze this circuit quantitatively based on your reasoning and the analytical approach, and write your answer, what kind of circuit is this, in the comment section. So till then, wish you happy learning.